So I do have a little something for you today, and it's based on the Pythagorean theorem. And you know, almost everybody, especially if you're in school, will know or remember what the Pythagorean theorem is. And if you ask them, they'll say, oh yeah, that's a squared plus b squared equals c squared. Well, if you remember what a, b, and c are representing, yes, that's true. But before we get going on that, do you know why it's true? And everybody says it all the time. It seems kind of, I don't know, like a lucky coincidence, doesn't it, that the numbers work out that perfectly? So I'm going to show you why it's true, and thanks to our graphic artist, I don't have to say a word. Check it out. So now you're a believer, right? Now we all know why it's true. Actually, if you, I think there's hundreds, if not thousands, of different ways to prove that that is true. But that's one of the nicer ones, because as I mentioned, I didn't have to say a word. You could just watch the pictures and see that, yep, it really works. So if you're in a math class and you use the Pythagorean theorem, usually the questions are, they give you a right triangle, and they say, okay, you know, we'll give you some measurements, and you have to figure out what the other side is. Well, maybe you didn't realize this, but you can actually use the Pythagorean theorem in reverse. See, the Pythagorean theorem requires a right triangle. That means you have to have a right angle in it, a 90-degree angle. But you can also use the Pythagorean theorem in reverse to create right angles. So what I was going to show you today was a way to do that, and this is actually used by, for example, archaeologists. Archaeologists, if they're out there in the desert digging, you know, and they're trying to dig up artifacts or something, sometimes what they do is they want to keep a careful record of where they find all this stuff, because they're going to, of course, dig it out and study it, and they want to have a nice version of where they got all these things besides just a photograph. So what they often do is they lay out a grid on the ground, almost like a graph, and they can give everything coordinates. So they can, you know, take a record of where I pulled this object out of. Well, how do you get a nice perfect rectangle with nice 90-degree angles on the ground that's all bumpy and not even level? And it's actually a little harder than you think. You can't just, you know, eyeball it or go take a little protractor on the ground and get it to come out good. So what they can do is use the Pythagorean theorem. So I'm going to show you how that works. And we'll do a little computation ourselves, but I have set up my own little archaeological dig on my math cam here. So what I have, so I don't know, let's say, okay, this is a little urn you have, you're going to dig up, you know, and you got some other things in here. So what they're going to do is I want to make a rectangular grid out of this thing. And so I'm pretending that I have a shrunken scale here. This is a tape measure, and I want to make a grid that's 14 feet by 10 feet. And I want to get the right angles perfect. So like I said, it's not very easy to do by eyeballing. So what I could do is take my tape measure here, and I'm going to measure out 14 feet right here. And I put 2 pegs in here, and I have some string that's representing rope. This is what they would do, you know, if you're out in the field. They would take some rope and measure off 14 feet. Now the question is next, I want a 10-foot rectangle. So I want a side here that's 10 feet. And I have my tape measure I made out. The problem is, how do I know exactly where to put this so it's a nice 90-degree angle? And it's hard to guess. And once I measure, I have some rope here I'm going to stretch over to that much. So the idea is you can use the Pythagorean theorem to do this. So what we could do is, I'm going to actually use this diagonal right here to see how long it should be. So let's do a little computation and see how long the Pythagorean theorem says this diagonal length should actually be. So I'm going to sneak a piece of paper in here. I'm going to do a little measurement here because I do have a right triangle, and I want 14, 10. The question is, how long should that diagonal side be? And if you've had this in class at all, you might remember this is called the hypotenuse. So according to that Pythagorean theorem, this could be side A, the 10 could be side B, and the hypotenuse must be that letter C that was in the formula. And then we're going to go ahead and actually compute what C should be to make this work. So let's see what I got here. I got 14 squared, B is 10, and C is, well, I don't know what it is, so I'll just leave it as C for now. All right, let's see, that's 196, 14 squared. This is 100. And if you add those together, it's 296. So whatever c is, all I have to know is I just need to take a square root of both sides, and the square root of 296 is exactly what that diagonal measurement should be. And I did this on a calculator ahead of time. It's about 17.2. So what I'm going to do to create a right angle is I'm going to measure a rope 17.2 feet long and pull it diagonally across, and that will actually make me adjust the exact angle I need in the corner. So I did this on my miniaturized tape measure again. You ready? Here's my, my tape measure, 17.2. So what I'm going to do is on these little ropes I have, I'm going to mark 17.2 feet. So here's my little rope here. I'm going to measure this out 17.2, and I'm going to mark it. So 17.2 is right here. All right, so I marked that on the string. Okay, and I'm going to do the same thing to this string over here. So I'm going to measure this 10 feet up, and I'm going to mark it. So it's about right here. All right, I have my measurements. The idea is if you adjust these ropes so that these things match up, these little dots I made, you will have a perfect right triangle, and that means you have a perfect right angle, and it happened right here. So hold on, I have a little marker I'm going to put in there. That's all I needed the triangle for, just a temporary measurement, so I don't need it anymore. If you now take this angle down here, you'll see it's a nice, perfect 90-degree angle. And if I do this again, I could take this string over here and make my perfect rectangle if I do it again in this corner, and you would have pretty much a perfect rectangle sitting underground. And then you can go take all your records and dig up your urns or whatever else you're digging up. So I thought this was interesting because in classes you always do the other way. They give you a triangle with a missing measurement, but I don't remember them actually using these to create a nice 90-degree angle. So there you go. If you're building something, I don't know, building a house, who knows. Now you can create a perfect 90-degree angle. You don't even have to go to the Home Depot and buy one of those squares or anything. You can do it all just with some measurements. Well, today I was going to show you a little bit about, maybe you've been hearing about these storms back east. And if you're a local here in San Diego, it was like, I don't know, it felt like 75 degrees outside today, so we have nothing to complain about. But back east, it isn't looking so good. In fact, I have a headline I pulled up on my computer from the New York Times. This is Chicago from just a few days ago, and they've been having record lows, I believe. I don't know if they're a record, but it was a pretty bad snowstorm they were having. And I have the weather report for tomorrow, and what you might have heard them say is something about the wind chill. In fact, this is the wind chill chart published by one of our government agencies, the National Weather Service. And so what is this wind chill? I'm just going to show you there's actually a mathematical formula attached, of course. The wind chill, you probably can't read those little tiny numbers there, but I have a formula for it on my, my little math cam here. And what the wind chill does is it accounts for the wind and the cold. So if it feels cold outside and it's actually windy, the wind makes it feel colder to your face. So what they will do is say, well, the temperature, the thermometer says it's a certain degrees, but actually, with the wind, it actually feels this much to your face out there in the cold. So this is the formula they have for it, and it looks kind of long and complicated, but I've marked there's two actually input variables here, which might be a little unusual for you if you've only had some algebra classes with functions in them. So if you look at this formula, there's a T in there, and that stands for the actual air temperature you'd see on a thermometer, and there's also a letter V, V for velocity, that's the wind speed. In this formula, it's miles per hour. And if you use this formula, you can generate the amount of wind speed, or the wind chill rather, the effective temperature you would actually feel if you were standing out in this particular weather condition. So I looked up on the web the weather report tomorrow for some of these cold areas, and I took a picture of it on my computer. Here it is. And if you look up towards the upper right, it says that tomorrow, it says Arctic blast coming. It sounds dramatic, I know. This is from the Weather Channel, by the way. On the upper right, it says Chicago is going to be 15. That's the high, a high of 15. So I also checked on their expectations for wind tomorrow, and they expect the winds to be a maximum of 25 miles per hour. So I thought, let's say you're standing outside in Chicago, it's 15 degrees, which is their high for the day, and imagine the winds blowing at 25 miles per hour, which is the most they predict might happen tomorrow. What would the wind chill be? So I have this formula, and I'm going to put in those particular values. So for T on my formula, that was the actual air temperature, I'm going to put, it was supposed to be 15 degrees tomorrow in Chicago. And then for V, the wind speed, it was supposed to be up to 25 miles per hour. And all I have to do is put those values in this little formula here, and we're going to get a number. Now, I punched this ahead of time in my calculator so you wouldn't have to sit there and watch me push all the buttons. So I have this big, long string of numbers punched in there. What I've done is, for T I put 15, and for V I put 25. And my calculator says,
drum roll please, that this is about -4. So what that means for us is that it should feel like about 4 degrees below 0 if you were standing out in that weather in Chicago. So if you're a local, doesn't that make you appreciate our nice weather here, even though it's a little chilly at night? They probably wouldn't think so back east, right? So one interesting thing about this formula, I mean, it's interesting because it has 2 inputs, but you can actually, if you know a little bit of calculus, you can actually do a derivative with it still if you don't let both of the inputs change at once. So for instance, what we could say is, okay, if you're in Chicago, what would happen if the temperature stayed at 15 degrees, but the wind actually kicked up and got more strong? So what you could do is put 15 into the formula. In fact, I'm going to do that. I'm going to put 15 into the formula. So we'll say fix t equal 15. And you actually get a simplified version of the formula, which I wrote down ahead of time. Here's what it would say. And by doing this, you actually get a formula with just one variable in it. So it's kind of like we converted. We said, you know, really we had 2 inputs here, but since I'm going to pretend that the temperature doesn't change, it just stays at 15, we're just going to leave it at 15 degrees. And that way, I only have one input in my formula changing. And from here, if you do know a little bit of calculus, you could actually do a derivative, and that would measure how the wind chill would change according to the wind speed changing. So we're going to do that real fast, just for the calculus folks out there. So what I'm going to do is take a derivative of the wind chill with respect to the wind velocity or speed. And it's a pretty easy derivative, actually, once it's all simplified. So the 45 number here is just a constant, so that becomes 0. And then let's see, the 29.3375 is a constant out front, or coefficient. And then this is a power of v. So if you've learned how to do derivatives, the 0.16 would come down, and you would subtract 1 from the exponent. So let's see, 0.16 minus, say 0.16 minus 1 would be, I believe, a negative 0.84. So this is the rate of change with respect to wind speed of the wind chill. So you try and picture what we've got going on. We've actually fixed our value of the temperature at 15 degrees, and now we're going to imagine the wind speed is going to increase, and what we want to know is what effect will that have on wind chill. So all I have to do now is put in this value of v, which is 25 miles per hour, and I did this ahead of time, and it comes out to be approximately negative 0.3. So what does that mean for us? Well, negative 0.3 means if the wind goes up just 1 mile an hour, your apparent temperature is going to drop 0.3. Or another way you could say it is if the wind went 10 miles per hour faster up to 35, you're going to feel a drop of about 3 degrees Fahrenheit in temperature. So this gets more extreme as you get colder and colder and colder. And if you go to the National Weather Service website, their chart tells you how long you can last until frostbite kicks in and makes an unpleasant end for you. So in the theme of Thanksgiving, I do have a little math to show you about cooking turkeys. So I didn't bring a real turkey with me live or from the store because it wasn't very convenient, but I do have a picture of what you might be seeing in 2 weeks. Well, hopefully that's not what's on your table, actually. How about this? Does that look a little better? So I know a lot of you are going to be eating a lot of turkey in 2 weeks. So here's what I have for you. If you put your turkey in the oven, it takes a long time to cook. And I'm actually going to show you, wouldn't you know it, there's an equation that tells you basically how the temperature of the turkey rises when you put it in that oven. And it's maybe not what you think. It doesn't go linearly. In other words, it doesn't do a steady progression temperature-wise until it's ready to be pulled out of the oven. So we're going to do a little experiment here. I'll show you how this works. It's all based on equations used for exponential growth. And I have a reminder of what this equation looks like. You will see this in an algebra class or pre-calculus class or something like that, and calculus classes as well. And this goes for any relationship you have where there's a constant percentage increase. And this is actually the case when you put something in the oven. So if you look at that equation, the big letter C there is the initial amount, whatever you're measuring. K is the growth rate, and T is time. And we're going to use this equation actually to figure out what exactly is going on with a turkey once you put it in the oven. Now, if you've had some higher math, calculus at least, this is actually all based on a differential equation. What it says is the growth rate or the derivative is proportional to the amount present. So what that means is the more stuff you get, the faster it increases. And in a sense, this is what's going on with your turkey's temperature when you put it in the oven. It's actually based on something called Newton's law of cooling. Well, it's called cooling, but it applies to warming as well. And that's what we're going to do with our turkey. So I have a little scenario. I made it up, a little scenario with your turkey, but it's fairly realistic, actually. So what we're going to say is you have an 18-pound turkey, and you're going to take it out of the fridge, which is, we're going to say it's 40 degrees in your fridge. So right now your turkey is 40 degrees, and you're going to put it in the oven at 325, and we're going to see what happens to the temperature. And by the way, I don't want to misrepresent myself, because I'm lucky if I can cook microwave popcorn. So this is not coming off personal experience. I spoke to experts, though, that claim they know what they're doing. So this should be realistic. All right, here we go. So I got my turkey. So let's say at time 0, this is 0 hours. And I'm going to, let me see, I'll zoom this in so you can see that a little better. Okay, so at 0 hours, my turkey is 40 degrees Fahrenheit. Now, what I was going to do is give you an example of what it could be after an hour. And if you've actually ever tried to cook a turkey, they go kind of slow. So let's say after an hour, it's 82 degrees, which should be fairly realistic. What I want to do from here is try to figure out what the temperature is going to do, and then we're going to figure out how long it takes to cook the thing. And it's recommended that you pull the turkey out when the inside gets to be 180 degrees. So that's our target. We're going to see how long it takes this thing to get to 180 degrees. Now your oven is 325, which everyone I checked with said that's the temperature you want. So Newton's law of cooling says, it's a slight variation on what we already had. It says that the difference rather in temperature is actually what's proportional if you look at the relationship of what's going on with the turkey. So it's not actually the temperature itself, it's the difference with what it's surrounded by. So what we want to do is say, okay, at time equals 0, what's the temperature difference? And if you keep in mind that the oven's 325, and I'm going to put this 40-degree turkey in the oven, at time 0, the difference in temperature, well, it's 325 minus the 40 that the turkey actually is, and that comes out to 285. Now, after an hour, what's the temperature difference? So after 1 hour, well, the difference is, let's see, 325 is what the oven is, and we're going to say it's 82 degrees. So I did a little work ahead of time. That's 243 degrees. And believe it or not, this is enough information for us to estimate exactly what's going to go on with that temperature, even though it's not a linear relationship. And by the way, I should mention that this is a little bit simplified. There's a lot of things that go into this, like how big the turkey is and how dense it is. And I mean, actually, the flow of heat is a complicated thing, and I'll save it for some high physics class you take someday, maybe. But for a simplified version, this isn't going to do too bad for us. All right, so that equation you saw a minute ago that looked like this will work perfectly fine for us as long as you realize this is the temperature differences. So for example, this value of C, this is the difference in the initial temperature at time 0. So that's 285. And A is going to be the temperature difference as time goes on. K is the rate at which this is increasing, and I don't know that yet. That's what we have to figure out. But you know what? We have enough information. It's not going to be too hard to figure out. All we're going to do, we're going to take this formula I had, and we're going to put in the information I know after 1 hour. So for example, after 1 hour, I know that the temperature difference was 243, so I'll put that in for the A value. And I know C is 285, because that's what I started with as a temperature difference. And I have times E. K I don't know, but I do know that T is 1 hour at this particular temperature measurement. So I'm going to do a quick solving of this. We'll divide both sides, for example. So let's see, 243 over 285 is E to the K. This is going to require a little bit of logarithms, but if you haven't had logarithms before, it's okay. I'll show you what this comes out to be anyway. But basically, we're going to take logarithms of both sides, natural log, and on the right, I just get my value of K. So it turns out, I looked ahead of time, this is about negative 0.1594. This is your percentage growth rate in a sense. But what this allows me to do is put the equation back together. So here is the equation for the temperature difference of your turkey, 285 E, negative 0.1594 T. So I'm going to put this on a calculator. The only thing we have to account for is this is the temperature difference, A. So really, this is 325 minus, I'll call it a capital T, the temperature of my turkey. And I'm going to rearrange this a little bit because it's just going to put a nicer form and put on my calculator. And I'll show you a nice little graph, and I'll tell you when to pull your turkey out. If you trust my judgment over Betty Crocker or somebody else, we'll see. So anyway, I'm going to rearrange this equation slightly. So here's what you end up with. It's 325 minus 285 E, negative 0.1594 T. Now I put this in my calculator. I'm going to show you a graph of your turkey's temperature as time goes on. And you notice it's not a straight line. So in other words, if you look, it increases a little faster at the beginning, and then towards the right, it's going slower and slower. But what I want to do is see how long it's going to take to get to 180 degrees. So for example, this is 2 hours right there. If you look at the bottom right, it's 117 degrees. 3 hours, it's 148. 4 hours, 174. We're getting really close. I'm going to scoot to the right a little bit. Looks like about 4.2 something hours is how long it's going to take for that temperature to finally get up there. So this is actually fairly realistic in as far as how temperatures work once you cool something down or heat something up. They don't go linearly. They go in steps that slow down or speed up depending on what the temperature difference actually is. So I don't recommend actually doing your turkey this way because your friends will think you're a real nerd in there, you know, with your graphing calculator and taking measurements and graphing and seeing, you know. You probably should just go by the guidelines the turkey people say, but now you have a little more insight anyway. And this warm-up has to do with counting your calories. And you know, the holiday season's coming up and people tend to, I don't know, maybe eat a little more goodies than they should. So anyway, if you want to watch your calories, this will help out a little bit today. So here's the story. I went to the store, Trader Joe's actually, and I bought some packaged deli meat. And I was trying to figure out how many calories I was eating as I ate this stuff. And it wasn't so simple because, you know, on some things you buy, it's all, I don't know, prepackaged and it says, if you eat, you know, this many, you eat this many calories. Well, this was all by weight, and it turned out to be not quite as straightforward to figure it out as I would have thought. So that's what we're going to do. We're going to figure out how many calories I ate, and you can actually use this when you, you know, with any food you might eat, or actually you can use what we're going to do in many different situations. So here's a picture of the package I bought, and it's just, I don't know if you can tell, there's 5 slices of turkey in there, and I was going to say, let's just assume they're all the same, you know, size. So 5 equally sliced sizes in there, and you probably can't see the label. I know it's a little small on the screen there. So actually, I have it on my math cam here. Maybe we can, I'm going to zoom in. Let's see if we can see this here. If you look at this picture, I know the print's a little small, so I'll go ahead and summarize it anyway, but it says that the serving size is 2 ounces here, and then it says there's 60 calories in a serving. So a 2-ounce serving, 60 calories, and the problem is, it didn't tell me how many slices that was. So I'll summarize the information here for you. Basically what we have, see if it fits on the screen for you. I have 5 equal slices, and the package on the, I don't know if you saw that part of the other label, the package said it was 0.33 pounds for the whole thing. And then I know that a 2-ounce serving has 60 calories. So I've summarized this information on my, my little math cam here. So should be able to see that. And so the goal is, let's say I ate 3 slices of this turkey. I didn't eat the whole package. I wasn't a total pig. How many calories will I have consumed? And again, it just wasn't quite as straightforward as I thought, but there's going to be a good little practice here. And this is something you can use in computing lots of different things. All I'm going to do this in one big computation. I'm just going to convert from one unit to another, one step at a time. And the technique we're going to use, you can actually use in many different aspects of life. So if you want to convert any sort of measurement to any other measurement, you know, whether it's yards to inches or feet to mile or anything like that, you can use this technique. So what I'm going to do is we're going to start with the fact that I ate 3 slices here. And I want to end up converting that to calories. I want to know how many calories did I eat in 3 slices. So what we're going to do is we're going to go one step at a time, and we're going to convert slices to something else. And at each stage, we'll use some equivalence or some relationship that we know, and you'll see in the end, we actually are going to end up with the number of calories. And I'm not going to have to do a bunch of intermediate computations. We're just going to have this big string, and it'll show me exactly what to multiply, exactly what to divide, and in the end, we'll have our number. So what I want you to think about is, for example, if I eat 3 slices, what do we know about the slices? Well, if you look at my information up top, the only thing I was told was, if you eat 5 slices, that's the whole package. And I know how much the whole package weighs. So let's go ahead and convert. And what I'm going to do is I'm going to multiply by a fraction. And I want you to think of 3 slices as being on the top of a fraction. And I'm going to multiply by another fraction. And I don't want slices anymore. What I want is something else. So I want slices to cancel. And if you remember how to multiply by fractions, you can cross-cancel things on top to things on the bottom. So that's what we're going to do here. So what equivalences do we know? What do we know about slices? Well, I do know that there are 5 slices in my package of turkey. So I made a fraction, 1 package, 5 slices. Now, you have to understand what I'm really doing here. This fraction, in a sense, is equivalent to 1 because 1 package and 5 slices are the same, at least for this scenario. So I'm actually kind of multiplying by 1 written in a funny way. And we've written it in a way so that the slices will cancel. So in fact, I can go ahead and say the slices will cancel, and I now have one package. All right, let's keep going. I don't want package, of course. I want calories eventually. Well, what do we know about the package? The package weighs 0.33 pounds. So I'm going to convert one package to an equivalent weight, and that was 0.33 pounds. So look again what would cancel. I would have package cancel, and now I have pounds. So if I were to just stop here, I've converted 3 slices to pounds. I'm not done yet, though, of course. This isn't what I wanted, so we're going to keep working here. So let's do another fraction. I have pounds right now. I want to get rid of it. So I'll put pounds on the bottom. What other equivalences do you know? Well, I'm working towards a serving size, but if you remember, the serving size was given in ounces. So we don't want pounds, we want ounces. All right, let's use a fraction again to convert. How do you get ounces out of pounds? Well, I do know that 1 pound has 16 ounces. So this is an equivalent fraction. This fraction, in a sense, is equal to 1. And when I multiply, I would cancel pounds on top, pounds on the bottom. All right. I now have ounces. Remember, I want calories. Well, we're getting there. What I have to factor in now is serving size. So the serving size was 2 ounces. Okay, so let's convert from ounces. I know there's 2 ounces in 1 serving. Okay, look what cancels. My ounces are gone, and what I'm left with is servings. You know what? We're almost there because I know how many calories are in a serving. One more. I want to convert servings to calories. 1 serving, they told me, was 60 calories. Okay, so look what cancels. I got servings going away, 1 on top, 1 on bottom, and finally I am left with calories, which is exactly what I want. The advantage of this, I know it seems like a lot of computations, right, just to figure this out, but the advantage here is I don't have to think about, do I multiply by 60 or divide by 2 or 16 or 5 or what? It's all spelled out in the fractions. So I went on a calculator and I went 3 times 1 over 5 times 0.33 over 1, etc., all the way down this list. So at this point I'm not really watching the units. The fractions tell me exactly what to multiply and divide. And when I multiplied all this out, I got 95.04. So this is calories. So that means if I ate my 3 slices of turkey out of this package, I actually consumed about 95 calories. So I know it seems like a little bit of work to figure it out, right? But unfortunately, it wasn't spelled out very simply. So this technique will actually help you if you want to compute something like this, or actually, as I mentioned, there's lots of other things that this works for as well. I don't think it'll help you with your grandmother's cookies, unless she's been very careful with her weights and measurements and she has some nutritional information for you. But I don't know. Maybe you're not supposed to think about that for the next couple of weeks, right?